All right, so you guys know the fundamental theorem of calculus. All right, so you guys know this fact. Okay, so integration is sort of an inverse of a derivative. Okay, so if you take the derivative of a function and then you integrate that, all that has happened is the integral has undone the derivative. So the fundamental theorem of calculus, this just says that this has undone this guy, so you get gx, and then you apply the limits. That's the fundamental theorem of calculus. You guys understand that? So it's telling you, what it's telling you is the value of this integral, where the integrand is dg by dx, the value of this integrand is just the difference in the value of the function gx. Okay? Everybody understand that? All right. Now we'll use this and we'll apply it to our situation. Okay, so let's say you're pushing on a box. Okay, so here at this position, that's the force you applied, and it moved dx fx dx. So the work done for this stretch was fx dx, okay? And then the work done for the entire distance was, this force kept changing, okay? And so it's just this integral. That was the work done. Okay? So when you calculate the work done, you are doing this integral. Okay? So, well, what has that got to do with the fundamental theorem of calculus? So this doesn't look like that. So what we're going to do is we're going to consider cases where, what if this force is equal to du by dx, is the derivative of some function. And that's what this chapter is about. Do you guys understand that? Okay. Everybody? All right, so the work done by a force is fx dx, this integral. Okay? From x initial to x final. You understand that, right? What if fx is equal to dux by dx? All right, so let's do the integral. So what if your force can be given by that function, the derivative of a function? Then the work done by your force is du by dx. Do you know how to do this integral? This is what the fundamental theorem of calculus tells you. If the integrand is a perfect derivative, then the integral is just gx. Okay? So this integral would be just u, evaluated at x initial and x final. So you see that integral was so easy to do. All he had to do was actually just evaluate this function at the endpoints. Okay? So if your force is like this, life is easy. Okay? So if your force is like that, then you're happy. Yep. So we even give it a special name. Yeah, you You guys like my smiley? It's not bad, actually. What's that? The smiley function. Okay. All right. If your force is like that, we give it a special name. It's called a conservative force. What is a non-conservative force? Oh, I'm sorry? That's right. So something that doesn't look like that. Okay. So a non-conservative force is some force that cannot be represented like that. Okay. There are only three forces that can be represented like that, that you will see. The spring force, gravity. So you've already seen the spring force. Gravity you'll see in chapter 13. And the third force is the electrostatic force. Okay.
And these three are the ones that are conservative forces?
These are the ones that are conservative forces. So can you give me an example of a non-conservative force?
A democratic force.
A democratic force. All right. So what is a non-conservative force? Friction. You pushing on a cart, normal forces, and so on. So there are so many forces that cannot be represented like that. Okay. So what is what is the great thing about these? So this entire chapter is dedicated to these three forces. Okay. And all these three forces are, these forces can be represented as the derivative of a scalar function. I'm doing it in one dimension. We'll generalize this to three dimensions at the end of the chapter. Okay. And now what we'll do is, for convenience, we'll introduce a minus sign. So we'll say your force is minus du by dx. Okay. So this will be minus du by dx. So there is a negative sign there. Okay. All right. Let me show the example of the spring force. What is the spring force? Minus kx. You guys remember this? Again. So what does that mean? So here is the x equal to 0, and when the object is at position x, the force is in this direction. Okay. When x is positive, so what is this saying? This is saying when x is positive, the force is negative. Okay. So you see this force, the spring force, as a function of position, is that. Okay. And what is that equation telling you again? When x is negative, negative of negative, the spring force is positive. Okay. All right. We call this force, what kind of force is this? I'm sorry?
Conservative force?
It's a conservative force. Okay. If it's a conservative force, what should be true? I'm sorry? Very good. It's the derivative of a function. And so let me show you. fx equal to minus kx is negative derivative of this function. Okay. So let's make sure of that. Okay. Derivative of that function. Derivative of x squared is 2x. 2 will cancel that. And so you get kx there. And so you get this minus kx. Okay? Indeed, this spring force. Did you guys understand that? All right. So going back. Okay, so force is conservative when it can be given as the derivative of a scalar valued function, and this guy is called the potential energy function. Yeah. So I know this slide is very busy, but I wanted to summarize this before I get into the slides because that's the essence of the chapter, and I want to make sure you understand it before we get into the slides. Okay. Everybody understand that? Any questions on it before I proceed into the slides? How's the right side of the class doing? My right side. No. All right. So again, if you want to calculate the work done by a force for an object moving in one dimension, that's the integral that you do. Okay? And in general, that integral might be hard to do, but for certain special forces, if your force can be written as the derivative of a scalar function, then that integral is very easy to do, and that's the point of this chapter. Okay? So the work done by such forces is just the difference in the potential energy function. Okay? It's the negative of the difference in potential energy function. Okay? All right. And so what are the three forces? Spring force, gravity, and electrostatic force. Okay. So here, let's calculate. Here's one other feature that I'll show you about the integral. Okay. So the spring force is given by that derivative. Okay. So, and this is the potential energy function for the spring force. So this is your potential energy function. Yeah. All right, so let's calculate the work done by the spring force. So let's do a drawing. Okay. Okay, so the work done by the spring force when the object goes from this initial spot to that final spot. So what you've done is this mass was compressed and then the mass is going from here to there. And what you're trying to calculate is the work done by the spring force when the mass goes from here to there. Okay? And what is that work done? It's this integral from x initial to x final. But your spring force is what kind of a force is it? It's a conservative force. It's minus du x by dx. And it was equal to ux x initial to x final. We already had this expression. I'm just re-deriving it for you guys. What was the spring potential energy function? 1/2 kx squared. So you calculated the work done by the spring force when the object went from here to there. And what was that work done? So here's a very important fact. It was equal to this. Everybody understand that? All right, so now watch this.
Can you repeat that? I'm sorry.
What you calculated was the work done by the spring force when the object went from here to there. and that work done was equal to minus 1/2 kx final square minus 1/2 kx initial square. So you see the work done just depended on the value of the function at the final point and the initial point. You agree with that?
Yes.
All right, so now watch this. I might even give you a donut if you reply this correctly. Maybe. What was the work done for this path?
Same thing.
Exactly the same. What was the work done for this path?
Still the same.
Exactly. You start and end in the same place. It doesn't
There you go. How many different paths are there? Infinite. That's the beauty of it. So for conservative forces, the work done just depends on the initial and final configuration. It's independent of the path. Okay, so you'll hear that definition as well. Okay. Did you guys understand that? How many forces are conservative forces that you will be learning about? What are the three?
Electrostatic, spring force, and gravity.
And spring. Okay. So we've dedicated a whole chapter to these forces just because it makes life easy for us. Okay. How did it make life easy for you? Calculating this work integral was a piece of cake. Okay. All right. You guys understand that? Any questions before we get into the slides? Because I'm going to buzz through the slides. Okay, so what is the potential energy function? So if a force, okay, so this is for one dimension. If a force can be expressed as like that, this guy is the potential energy function. And this guy is the force. And like our friends told us, there are only three forces that we'll deal with that can be done so: spring force, gravity, and the electrostatic force. And for these forces, you cannot do that. For friction, normal force, you pushing on something, and so on. Tension. Okay. So there are all these forces that you encounter for which you cannot do that. Okay. Those forces cannot be represented as the derivative of a scalar valued function, of a potential energy function. Okay? So if you wanted to calculate the work done by these forces, you have to do the integral. Okay? And good luck to you guys. All right. All right, so conservative forces. What are conservative forces? Forces that can be represented as the derivative of a function like that. Okay? Work done by conservative force on a particle moving between 2 points is independent of the path. Okay? So for instance, here's what that would mean. Okay? Is gravity a conservative force?
Yes.
Yes. So the work done by gravity in going from here to there would be independent of the shape of this slide. Okay, so let's say this was a frictionless surface. The only forces acting on it would be gravity and the normal force. Does normal force do any work? No. Okay. And then only gravity is doing work, and since it was independent of the path, the speed at which the ball comes out here would not depend on the shape of the slide. That's what that means. When friction is not present. Okay? Now, if friction is present, friction would do work dependent on the path, and so that would change things. Okay? All right. Friction is a non-conservative force, so the work done by friction will depend on the path taken. Okay? So non-conservative forces are such that they cannot, those forces cannot be written as the derivative of a scalar function. Yeah? You guys understanding this? I'm introducing the terminology all over, but okay, so for a conservative force, spring, gravity, and electrostatic force, you can define the potential energy function, and you already know what that potential energy function is. This guy is the potential energy function. Okay? And this guy is the conservative force. Okay. So gravity is a conservative force, and so you can define gravitational potential energy. And so here's what happens. We've all played some kind of ball game. All right, you kick a ball, it has kinetic energy, and if there is no friction, as the ball rises, kinetic energy is getting converted to potential energy, and then that potential energy gets converted back to kinetic energy. Okay? So if there was no friction present, when the ball comes back to the same level, it'll be going at the same speed. Okay? And in fact, at every point, the sum of potential and kinetic energy will be constant. You'll learn that. Okay? All right. So when you toss an object, the only force acting is gravity. We're assuming there's no drag force. Okay. So when only gravity acts, the work done by gravity can be easily calculated like that because it's a conservative force. It's the negative of the change in potential energy. Okay. So we'll give you the expression for the potential energy. So the work done by a conservative force is negative of the change in potential energy. Okay. So I will explicit only for conservative forces. Okay. So potential energy can be defined when dealing with conservative forces. Okay. So for conservative forces, the work done is equal to that. And why could you do this? Why was this possible? Because conservative forces are the negative derivative of a potential energy function. That's the only reason you could do that. Okay? All right, so for conservative forces, yeah, change in work done is negative of change in potential energy function, negative of U final minus U initial. Okay? And so change in potential energy is negative of work done. And in one dimension, the work done is given by this integral. And in 3 dimensions for a general trajectory, it's a line integral. Okay? And we will come to this in 3 dimensions. Toward the end of the chapter, we'll define this. For a 3-dimensional force, conservative force, it's given by the gradient of a potential energy function. How many of you know what this is? Let's see a show of hands. Okay. Nobody's in Calc 3? Okay. So we will, so I will show you what this is. So you'll know by the end of the chapter, okay, what this is. Okay. So in 1 dimension, the force was given by minus du by dx. Okay. So in 3 dimensions, this is sort of a generalization of the derivative. Okay. It's called the gradient operator. Okay. And we'll see what that means. called the gradient operator. Okay, and you'll be experts at it by the end of this chapter. Okay. So for conservative forces, change in potential energy is negative of the work done. And in one dimension, here's how you calculate the work done. In 3 dimensions, here's how you calculate the work done. Okay. All right, so now we will find the expression for gravitational potential energy. And here's the expression for gravitational potential energy. So gravitational potential energy changes in that direction. And generally, we call that direction y. So I'll give you the expression for gravitational potential energy in terms of y. It will be mgy. So the gravitational potential energy of a mass m on Earth is that. And this works close to the surface of the Earth. Close to the surface of the Earth, meaning within 10, 15, 20 miles. If you jump higher than that, then you'll need another expression. If you jump 100 miles, then you'll need another expression. Okay? Okay, so work done by the gravitational force, okay, is negative of change in potential energy. Here's the gravitational force, and you see what this is saying is, this is the J is the unit vector, the gravitational force is in this direction, and that's equal to minus mgj. So there is the gravitational force, and any displacement in that direction is dyj. dyj. Okay, so let's say you go from any initial point to a final point. This could be an initial point, that would be final, or initial to final, it doesn't matter. Okay, and you do this integral. J dot j is 1. Okay, and so this would be, I'm pulling out the minus mg dy. Okay, initial to final, minus mg is a constant. So, and the integral of dy is just y. Okay. Initial to final. So minus mgy final minus mgy initial. And that is the potential energy function. Okay, so U, the potential energy function, is mgy. So the gravitational potential energy is mgy. Yeah. When is this valid? Okay, when we were doing the integrals, you see you pulled out g. When can you pull out g? If it's a constant. Okay, so the radius of the, what is the radius of the Earth? What's the radius of the Earth? I'm sorry?
Half the diameter.
We got a smart ass. At 4,000 miles. And so if you rise up by, let's say, 1% of the radius of the Earth, that's small compared, g will be constant. So you jump up 40 miles and you'll be fine. Okay? And this expression will be good. G won't change. Okay? And but if you jump up 400 miles, okay, that's higher than the space shuttle, then G will change. Okay? All right, so as long as G is constant, so if you don't jump too high, then this expression is good. All right, so here's where we stand. Okay, what are conservative forces? So this is just a reminder. Conservative forces are Fx is forces that can be represented like that. What are the 3 conservative forces?
Spring, gravity, and electrostatic.
spring, gravity, and electrostatic. And what we are doing is, so those are the forces, and what we are doing is giving you this potential energy function for these forces. And I just gave you the potential energy function for gravity. Okay? So now what we're going to do is give you the potential energy function for the spring force. Okay? This thing you have to wait till next semester. Okay? But so the spring force now we'll show you is 1/2 kx squared. Okay? And if you wait, when you get to the next semester, Q1, Q2, R is the distance between them. The potential energy is minus KE Q1, Q2 divided by R. Okay, but you have to wait till next semester to see that expression. Okay? So what are we doing now? We're just giving you the potential energy function for these three forces. So we derived that. Now let's do the derivation for the spring potential energy. Okay? You guys understand? All right. So now we'll consider the spring force. Okay, so here's a mass attached to a spring. Okay, as the object moves from here to there, some initial point to some final point, the work done by the spring on this mass, the work done is given by this spring force, the integral of that, and that's equal to negative of the potential energy, change in potential energy. Okay, so now let me do that integral. Work done is minus k is constant. Okay, help me out with what is the integral of x? What is the integral of x, my friend?
1/2 x squared.
Very good. Okay, so minus k x squared by 2, right? And you're going to evaluate that between x and the final point. So minus 1/2 k x final square minus 1/2 k x initial square. So you see, work done by the spring force is the value of this function at the final point, value of that same function at the initial configuration. So this is your potential energy function. Okay. Okay. So the spring potential energy is given by 1/2 kx squared. Okay. Now notice it's a quadratic function of x. So if you stretch the spring by 1 meter there, the potential energy is the same as if you compress it by 1 meter. Okay? It just depends on the absolute distance from the equilibrium position. Okay? So the spring potential energy is given by that. And we are done. Okay? So what was this chapter about? This chapter was about forces that can be given as the derivative of a potential energy function. These are the two forces you'll see, and there are the potential energy function. What does it do for you? If you have to calculate the work done by these two guys, it's very easy to do. It's just take the difference in this potential energy function. Right? The work done by those guys is minus u x final minus u x initial. It's that easy. Okay? And that's what this chapter was about. Okay? All right. Now, we'll define something called mechanical energy. Okay? Now, the rest is all just terminology and stuff like that. Okay? So, let's try and understand some physics. So, mechanical energy. Mechanical energy is kinetic energy plus potential energy. Remember, the potential energy we represented it by U. Yeah? All right. what is kinetic energy? What's the formula for kinetic energy, my friend? You knew it when you were born. Okay, help him out. 1/2 mv squared. Okay, so sum of kinetic plus potential energy is mechanical energy. Okay, so here's the deal. Let's say there are only conservative forces acting on the system. Okay, for instance, let's say there's only a spring force acting on the system. The work done by that conservative force, okay, the net energy work done is change in kinetic energy. So this is the work energy theorem. Okay, and if there's only conservative forces acting on the work done by conservative forces, negative change in potential energy, that's equal to change in kinetic energy. So for instance, if gravity was acting minus, if gravity is the only force acting, work done by gravity is equal to this, and that's equal to that. Minus of minus is plus. We'll bring that over here. So initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. That's what this is saying. So when only conservative forces act, the sum of kinetic energy plus potential energy at an initial point is equal to the sum of kinetic energy plus potential energy at the final point. What is the initial point in our diagram? What is the final point? Doesn't matter. You can take any point to be the initial point, any point to be the final point. So what this statement is, it's a pretty powerful statement. The sum of kinetic and potential energy at every point remains constant. Okay? All right, so this helps you solve problems that are sometimes hard to solve using Newton's laws. Okay? So, and when is this true? When is this true? When only conservative forces act. Okay? So what does that mean? That friction is absent, you're not pushing on anything, Elon Musk's rocket is not doing any work, and stuff like that. Okay? So this thing works when you toss a ball, there's no drag forces and stuff like that. Okay? So when only conservative forces act, mechanical energy is conserved. All right, so when only conservative forces act, mechanical energy is conserved. So that means the mechanical energy of this object falling down is the same at all locations. Okay, okay, so this is what's illustrated here in a roller coaster. As the roller coaster is rising, its gravitational potential energy is increasing, its kinetic energy is decreasing. Why is its kinetic energy decreasing? Because it's slowing down. Okay? And then as it falls down, its potential energy decreases, its kinetic energy increases. Okay? But if there was no friction, the sum of these two guys, mechanical energy will remain constant. Okay? So that's what that's showing you. Okay, when only conservative forces act, mechanical energy at a final point is equal to mechanical energy at initial point. So I bring this over here, change in mechanical energy is 0 when only conservative forces act. When non-conservative forces act, they change mechanical energy. Okay? So what are non-conservative forces again? I keep forgetting. Friction. I'm sorry? Tension, you pushing on it, and so on. Okay? Elon Musk's rocket, and so on. Okay, those are all non-conservative forces. So when non-conservative forces act on a system, they change mechanical energy. Your car engine's force, it's changing the mechanical energy of your car. Okay? So if you do positive work, then you're increasing mechanical energy, and if you do negative work, you're decreasing mechanical energy. So when you apply brakes to your car, you're decreasing mechanical energy of your car. When you're accelerating, you're increasing mechanical energy of it. Okay? Now it turns out that friction is one of them, and the work done by friction is easy to calculate, so we separate that. So here's other mechanical energy, and here's work done by friction. What does friction do to mechanical energy?
Takes it away.
I'm sorry?
It reduces it.
It converts mechanical energy to heat. Okay? So if friction did this, friction always does negative work, and the negative sign telling you it's decreasing mechanical energy. Okay? It produced that much heat. It converted that much mechanical energy to heat. Okay? So all the non-conservative forces change mechanical energy. Heat in particular converted it to thermal energy. Okay? So this is just saying other non-conservative forces change mechanical energy and thermal energy. Okay. Anyway, don't worry about all that. Okay. So for an isolated system, so if you have a system, you leave it to itself, and there's no external forces acting on it, then change in mechanical energy plus change in thermal energy plus change in internal energy, the sum of all those changes is zero. That what we are saying is, for an isolated system, the total energy of the system remains constant. Okay, that's the statement. And this is the conservation of energy statement. Change in total energy is zero. Okay? All right. So we've tested this for large systems, and for as large as a system as we've tested, that's a true statement. Okay? So for an isolated system, the total energy of the system is zero. I mean, the change in total energy is zero.
So what's considered an isolated system?
So what is the largest isolated system that you know of? So as far as we know, total energy of the universe is constant. Okay? No. But as far as we know. Okay. So for a conservative force, how do you calculate the force? What was the expression for the force? Fx was equal to minus du by dx, right? You guys know how to take a derivative? Yes, you do. You're all experts. Okay? So if you know the force acting on an object at any location, you can predict its motion. Okay? Force is mass times acceleration. And acceleration, like our friend said, is second derivative of position as a function of time. So if you know the potential energy at any location, I mean, if you know the potential energy function, you know the force everywhere. And once you know the force everywhere, you can calculate the acceleration of the object. So you can calculate its trajectories and all that. So what we are saying is, if you know the potential energy function for a system, you know the behavior of a system. You can calculate the behavior. Okay? Okay, can you predict my behavior? No, because my behavior doesn't have a potential energy function. This guy attached to the spring, he's got a potential energy function. Okay? All I have to do is to describe the behavior of this guy, all I have to give you is this potential energy function. I know exactly, no matter what you do to him, I know how he'll behave. Okay? So you see, this is a pretty neat concept. Here's a system, and the only thing you need to know about this guy is this potential energy function. And you can calculate the behavior of this guy. Okay? So if you want to describe a system, What do? All you do is throw the potential energy function at somebody. Okay. Can you do that for all systems? No. If there is friction in a system, you can't do that. What's that? No democratic system. Okay. So only for systems where conservative forces act. Okay. So given the potential energy function, you can calculate the behavior of the system. Okay. So for systems where only conservative forces act, you can give potential energy curves. So for a mass attached to a spring, here is the potential energy function. Once you have the potential energy function, you can calculate the forces on the system, and you can calculate the behavior of the system. Okay. So here's a potential energy curve. What has somebody done for you? They've described a system's behavior completely like that. Okay. So this would work, for instance, if a marble was rolling down a hill like that. Okay. And so, see, you intuitively knew how to solve all the differential equations. Let's say I take a marble here, and there's no friction, and I drop it. What will the motion of the object marble be? It'll roll down, go that high, then what does it do? Rolls back, goes there, and it keeps doing that forever. You didn't have to solve any differential equation. You intuitively, you knew that. All I gave you was this curve. Okay? So that's the power of this thing. Okay? What if I drop it from here? You know it'll roll over that curve, go up to there, and there. Okay? So based on the initial condition, the motion will be different, but you knew all of that. All I had to do was throw this curve at you. Okay? And you knew the behavior of the system. All right, so that's the power of these potential energy curves. But you can only do that for, when can you? When only conservative forces act on the system. Okay? All right, now we'll generalize the concept to 3 dimensions. Okay, so in one dimension, if I gave you the potential energy function, you knew how to calculate the force. Minus du by dx. Okay? Now, how do we generalize that to 3 dimensions? Okay? What was this guy? This was the potential energy function. Okay? Energy, by the way, is it a scalar or a vector? Scalar. So this guy spits out one number. Okay? So that was in 1 dimension. Now let's do it in 3 dimensions. Okay, so now let me give you a scalar valued function in 3 dimensions. Okay. What does this function mean? Yeah, so mathematically, what does this mean? I can give you x, y, z coordinates, and it'll spit out a number, right? That function will spit out a number. All right. So let's make up some numbers. For this point, for this coordinate, u is I'm giving you values for u. For this point, u is 105. For this point, u is 110, and so on. Okay. Have you guys done partial derivatives? Okay. Do you guys know? So I'm going to make this function up. X, y, z equal to x squared, y cubed, z to the power 4. Do you know what del u by del x means?
Just respect to x.
That's right. This is a partial derivative. Okay. Again, you got to concentrate for another 5 minutes. This is important stuff. You'll be learning this over several months in your calculus classes. So what this means is you treat the other variables as constants and you take the derivative only with respect to x. Okay? So this is, so help me out now. So y and z are constants.
Y cubed z to the fourth,
2x y cubed z to the fourth. Okay? What does del u by del y mean?
3x squared y to the second z to the fourth.
So x squared, 3y squared, z to the power 4. Yep. Del u by del z. You, my friend.
X squared y cubed 4z cubed.
Very good. All right, so what do these partial derivatives mean? Okay, let's go back to, okay. So if you calculate the partial derivative, if you calculate del u by del x is at this point, how is u changing when you move parallel to the x-axis? So del u by del x tells you how much u change when you move unit distance in the x-axis. Okay? Parallel to the x-axis. What does del u by del y tell you? How does u change when you move parallel to the y-axis? What does del u by del z do? It tells you how u is changing when you're moving parallel to the z-axis. Okay? And you can calculate it at any point. So that's what partial derivatives tell you. Did you guys understand all of that? All right, now we'll come to the gradient operator. Okay, so we understand all of this. Okay. So now here's the value of u coming back to this. So here's various values, so 102 and so on. Okay. Now at any location, you can ask the following question. Okay, in what direction do I need to move to find out? Okay, so if I move in this direction, u is changing in that direction. Let's say it changes 4 units per meter. If I move in this direction, it's changing 6 units per meter. In this direction, it's changing 8 units per meter. Now, I want to ask the question, in what direction do I need to move to find out the fastest rate of change? Do you guys understand that? So let's say you're going on a hike on a mountain, and you ask the question, in what direction do I need to walk for the elevation to change the fastest? That's the question. You guys understand? Okay, so the fastest rate of change of u. Now, the fastest rate of change has a magnitude and a direction, right? So it's a vector quantity. And that is the gradient operator. So the gradient operator del u by del x, you understand that? That's the partial derivative of u. I plus del u by del y, even I understand that. Yeah. And del u by del z, and Landon understands it. Okay, so the gradient operator is this guy. And what does it give you?
The fastest rate of change.
Very good, my friend. So this gives you the fastest rate of change of u, the scalar valued function. Yep. So it gives you the magnitude of this vector tells you the rate of change of u, and the direction tells you the direction in which it's changing the fastest. Yep. So that's the gradient operator. And what is this formula telling you? The force on the system at that location is pointing in the opposite direction. That's what it's telling you. So you take a potential energy function, calculate the gradient, and the force is in the opposite direction. Okay? So that's the generalization of this one-dimensional expression. Okay? All right, so we understand all of that. Okay, so there is, for the spring force, here is the force derived, shown to be the negative derivative. Okay? Now, I'm going to quickly here's Newton's second law. Okay. Quickly define some terms. Okay. When the net force acting on the object is zero, then the acceleration is zero. And then when the acceleration of an object is zero, it's said to be in equilibrium. Okay. So an object is in equilibrium when its acceleration is zero and the force acting on it is zero. Okay. So for instance, if this was a mountain or something like that, if a marble is there, the net force, the gravitational net force on it will be zero, okay? And it will be in equilibrium. It'll be in equilibrium here as well, here as well. So minima and maxima are equilibrium points. These are also equilibrium points. And these are unstable equilibrium. These are stable equilibrium points, and these are all neutral equilibrium points. Okay. So stable equilibrium points are local minima and absolute minima. Okay. Unstable equilibrium points are local maxima and absolute maxima. Okay. Neutral equilibrium points are regions of horizontal, okay, flat surfaces in the potential energy curve. Okay. Now what this is showing you is, so what is the gas in this room? Air. What is air made of?
O2, nitrogen.
Yeah, nitrogen and O2, essentially. I guess 78% and 21% of oxygen and less than 1% the rest of the stuff. Okay. So these are all diatomic molecules. Okay. So here's an oxygen atom, here's another oxygen atom, and here's a nitrogen atom. So and here's a nitrogen atom. Okay. So now the question is, how far apart are these nitrogen atoms? Okay. So what this curve is telling you is, okay, as you change the distance between them, it's giving you the potential energy as a function of r. Okay, the distance between the molecules. Okay. And when they're too close together, the potential energy is large, and as you pull them apart, as the distance increases, the potential energy decreases, and here is the potential energy minima. So if you take a marble, where does the marble end up? It ends up at the potential energy minima. Okay. So at the potential energy minima, at that distance is where the nitrogen molecules are sitting. And that is the bond length. Okay, so that's where the force on this atom is zero. Okay? So that gives you the bond length. And these are the various excited states and so on. Okay, vibrational states. So this curve tells you everything you want to know about the system. Okay, you can calculate all kinds of stuff. All right. I'm just going to come on. Okay. All right, so here's the question. Let's say here's a ball and it can.
Your signal's no longer, now it's okay.
Hmm?
It cut out briefly, you're fine.
All right, so let's say here's a slide, and it's a frictionless slide. And you want to build a slide to connect from this point to that point. The question is, what should be the shape of the slide such that you get from here to there the fastest? Should it be like that? Should it be a straight line? Huh?
It doesn't matter, right?
What doesn't matter is what speed it comes out with.
Oh.
What I'm asking is how to get there the fastest.
Straight down and curve over.
I'm sorry?
Straight down and then curve over, so it'll have the maximum velocity for the most amount of time.
So here's one curve. There's an infinite number of curves. Okay, that was the problem. Okay, and it turns out that the curve, the fastest curve is the something called the cycloid. And it's got very interesting properties. Okay, so it's not the straight line, that's what you would have thought, or this one, that's not what it is. The cycloid is the fastest curve, okay, but between any points. And that was this problem. So that's what, actually, let me show you. So you can see this. So here are two balls released. Here's the straight line path, and here's the cycloid. And you see the ball going on the cycloid got there first. So initially it's picking up speed faster than this guy, and once it's going fast, it gets there fast. Okay. So this is the inverted cycloid. Now here's a very interesting property of that curve. It's also a tautochrone curve. Okay, what that means is, so you might encounter this in your, you'll see this in your calculus classes as a problem. Oh. All right, so, huh? Oh, come on. What happened?
Oh, we got it on one screen.
Huh?
It's on that screen.
All right, so everybody go over there. What do you guys notice?
It all gets there at the same time.
No matter where you drop it, they're all taking the same time to get to the bottom of the curve. So that inverted cycloid is the fastest curve, and in addition, no matter where you start, it takes the same amount of time to get to the bottom. So very interesting curve, okay? Here are some interesting numbers on energy scales. That was the initial energy of the universe at the Big Bang and so on, okay? All right, so here's your daily food intake and so on. Annual energy use, the world uses actually 6 times 10 to the 20 joules per year. Okay? And your goal is to get this energy from solar and wind, okay, soon.